So I am sharing the screen. I hope you can see the screen. So in this session, I'll talk briefly about the wave mechanics, the quantum mechanics known as the wave mechanics. So this is all about quantum mechanics and particularly the wave mechanics. And please let me know if I'm not audible or if you cannot see my screen. So as I already told you, the quantum mechanics starts with quantum mechanics started because of all this development and explanation of all these theories like black body radiation, photoelectric effect, and also Compton scattering, and all this explain that electromagnetic wave is actually particles. They call it photon. And then the atomic spectrum and all the properties of elements in the periodic table describe that needed that electrons behave as wave, and that was in both cases the thing is called wave particle duality. In one old quantum theory, and the started with Louis de Broglie, and de Broglie postulated that wavelength associated with a particle of momentum p should be given by h by p, and this photon has energy E equal to h nu. Here nu is the frequency, E is the energy, and h is the Planck's constant. We'll have also h bar, which is h by 2 pi, and that's called the modified Planck's constant. We'll have it soon. But anyway, this is de Broglie's hypothesis is a wavelength of a particle. This is the wavelength associated with the particle wave, and this is the momentum of the particle, magnitude of the momentum. And if we call k, the wave number is 2 pi by lambda, then we get 2 pi p by h, which is p by h bar. And this is the wave number. And or we get momentum p is equal to h bar k in vector notation, or is called the wave vector also. This is the wave vector, and this is the momentum. And p equal to h bar k, and if I write down the energy will be h bar omega. Omega is the angular frequency. The omega is the angular. And this is the energy. And since E and P form a 4 vector, so we can say omega k forms a 4 vector kind of thing. And this is in the special theory of relativity. So I am not going there, but okay, I just wanted to mention that. And next, Next, I'll talk about the Schrodinger equation. So that was de Broglie's wave hypothesis. But then Bohr applied this wave hypothesis in atom, and the Bohr model was, if I have an atom, I have a nucleus, and I have an electron which is orbiting the nucleus. Then the electron wavelength must be integer multiple of the circumference. Drawing is not so good, but the idea is, again, if this is R, then the wavelength lambda by 2 should be integer multiple of the circumference 2 pi r. Let's start here. So wavelength lambda, not lambda by 2. So wavelength lambda is the integer multiple of I'm trying to lambda is equal to pi r, and from there I'll get the energy quantization for simple hydrogen atom. But this is not enough, so both Sommerfeld and then Sommerfeld modified this theory and circular plus elliptic orbit, and use the Sommerfeld quantization condition, that is P dot dr should be in h bar. This within the circular orbit. So basically, this is circle. So within the orbit, the momentum integration of the momentum could be position dependent, angle dependent. So that's the Bohr-Sommerfeld quantization condition. But actually, then Schrodinger postulated the behavior of these waves by writing down a wave function which is minus a squared by 2m Laplacian of the wave function, which depends on position and time, plus some potential which would be position and time dependent, psi of rt equal to psi h bar d psi. So this is the Schrodinger wave equation. Plus I h bar. This is the Schrodinger wave equation, but from where this wave equations comes? So I'll give you a brief idea of from where or how you can get these wave equations. But the historical development is this. Historically, I told you about this Fermat's principle of least time, Fermat's principle of least time for light rays. And then there was in classical mechanics, there is Hamilton's principle of least action. Hamilton's principle of least action and Hamilton-Jacobi theory. and also the wave uh, equation for electromagnetic wave. So just by comparing all these things, that if the same wave, which is an electromagnetic wave, can be described by a principle of least time, as Farmers did for light rays, and this light rays can be thought of as waving like particles, then Schrodinger came up with this equation where psi is he called the wave function. And he was not sure about the nature of the wave function and what is this wave function and things like that, but he gave this equation. Now this equation can be thought of as so we have the total energy E is the kinetic energy plus the potential energy, and the kinetic energy is p square by 2m, and the potential energy is v, and p is the momentum. So now this can be thought of as an operator equation, the Schrodinger equation, and from this equation we can so go to the operator equation, and the operator equation is like this. So if we can replace everything by some operator, so like I h bar, and so the operator will, and so the operator for energy will be I h bar, uh, and the operator for momentum will be equal to gradient of position. So so what is an operator? So first of all, so if I replace this with I h bar, an operator must act on something. So operator must act on a function, act on a function. So what is an operator? So operator is whatever. So like a very simple example of operator which acts on a function is differential operator. So I can use differential operator like D. This is nothing but an operator, and it acts on a function f of x and produces a new function which we called f prime of x. Like D acting on x square plus 3x will produce 2x plus 3. So it's acting on a function will produce another function. That is the basic meaning of operator. Now, if we have this energy relation in classical mechanics, then we can replace energy by this operator I h bar, which will act on some function, and this momentum by that operator. So we will get minus h bar square Laplacian by 2m, or p square by 2m, and also we will replace any function of r by an operator which will just multiply. So we can say this is an operator g of x. So let's call the operator g as g of x, which is nothing but acting on a function f of x will multiply with the function with another function g of x. So that is a kind of function identity operator times the function. So any operator b we can replace by something. So it must act on something. It must act on something, and we will replace b with the function, same function with will act on something by multiplication, simple multiplication, and what it acts on is the wave function psi. So from this classical mechanics, if we know what is the energy, we can go to the quantum mechanics, and actually it comes from the Hamiltonian formalism of classical mechanics. And what we have here is not energy but Hamiltonian basically, which is function of momentum and position. So so the procedure to get Schrodinger equation, from classical mechanics is I have a function Hamiltonian which is a function of r, p, and t. This is a function. This is my Hamiltonian function is equal to the age. Now I replace everywhere where a function which is a function of r by just scalar multiplication with p and function of r and t. Similarly, scalar multiplication, and with p by this operator minus I delta and h by the operator I h bar ddt. Okay, I missed the ddt here, ddt and I h bar ddt. So basically, that's the procedure to get the Schrodinger equation. So we have this simple Schrodinger equation, which is minus h bar square by 2m d2 psi of dx square. Now in one dimension, how the Schrodinger equation looks like, and psi is a position of x and t plus some function of b x and t. Psi position of x and t is equal to I h bar d dt of psi x n. First of all, this is a partial differential equation even for one dimension, because we have a time coordinate and a space coordinate. So it's always a partial differential equation. Second thing is the interpretation of the wave function. Interpretation is very important because the wave function is interpreted as probability density. So let's call the probability density as rho, which is x and t, and this probability density is depend on now we have a complex number here. I is the complex number. I is square root of minus 1. So psi will be complex. If V is complex scalar, psi has to be complex, because if V is real, if psi is real, then the left hand side is real. If psi is real, right hand side is imaginary. So psi cannot be real. So if V is real, psi has to be a complex number. So rho of xt is defined by the complex conjugate of this function psi of xt, complex conjugate, and this is the complex conjugation operator. And complex conjugation operator is again wherever you have I, you will replace that with minus I in the function. So if my function, for example, looks like e to the power I kx plus e to the power minus I kx with a and b coefficient, the complex conjugate function will look like. And if a or b are real, let's call a b real. Complex conjugate will be e to the power minus I kx plus b to the power plus I kx. So that's the complex conjugate function. Now, so this is nothing but the modulus of psi xt at each position and time square. And this is interpreted as probability density. So this is the probability density function. And what is a probability density function? Probability density function is exactly not probability. Probability density function is exactly not probability. So I have a probability density function x and t. So let's draw it for one position x for a given time. At some time t equal to t naught, I am drawing the probability density function. Something like that. Now the probability density function gives the probability as some x naught and x naught plus delta x naught, delta x, the particle to find at time t naught between x naught and x naught plus delta x. So the probability density function gives the probability of finding the particle at time t equal to t naught and in the interval x naught to x naught plus delta x. This total probability of finding the particle is given by this area. That is why it's called a density function, which is rho of xt dx. And so since the probability of finding the particle anywhere is always 1, since the probability of finding the particle at any time any time t equal to t naught and x belongs to minus infinity to plus infinity is always 1. So basically the area under the curve must be 1. And what is the probability of finding the particle between x1 and x2 is given by the area under the curve between x1 and x2. The probability of finding the particle here is given by x1, x2, rho of xt dx. So at t equal to t naught. So t equal to t naught, you will put t naught here. T naught. So since the probability of finding the particle is 1, we have the normalization condition on the wave function. Normalization condition on the wave function is psi star xt. Probability is 1. So psi star xt, psi of xt dx is 1 from minus infinity to plus infinity at all time t. Now I have this Schrodinger equation. Now let's suppose in this discussion that V is not time dependent. If V is time dependent, we have to do some kind of different treatment of the equations, which is known as a time dependent perturbation theory. So next we will assume that V is time independent. Next we will assume that V of xt is actually V of x, time independent. And I am doing it for one dimension. Moving to different dimension is very easy. Let's think about the time independent pencil. The first thing, the Schrodinger equation is linear. We have this Schrodinger equation minus h bar square by 2n dx square of psi xt plus v of x psi xt is equal to I h bar d dt of psi xt. The first property is linearity. Linearity means these operators are all linear operated. First of all, these differential operators or scalar multiplication are linear operated, and that is because these operators are all linear operators. So if psi1 of xt and psi2 of xt are solution of this equation, so their linear combination psi of xt is equal to c1 of psi1 plus c2 of psi2 is also a solution. So that's the first thing, linearity. Second thing is importance of the complex number. So if v of x is real, psi of x can be real. Because if v of x is real, psi of x is real, on the left hand side we will have real quantity, on the right hand side we will have an imaginary quantity which cannot be satisfied. So psi of x cannot be real. Third thing is completely deterministic in completely deterministic in the evolution of psi, in the time evolution of psi. Which means this is a completely deterministic in the time evolution of psi, because this is a first order differential equation in first order in time derivative. So if we know psi at some point t naught, at any time. If we know psi at some point t naught at any time, so know psi at some point t naught, then we can calculate, because this is a first order differential equation. Even this is even this is true without these assumptions, uh, but yeah, the linearity importance of I and time independence and complete determinism is true even without the assumptions that Vx is real. But so okay, we'll assume Vx is real because we'll derive more things now. So basically now if we know this, it says at each point x is, we know that what is the psi x naught at the next point, because we know the wave function at all position x. So this is x variable and this curve is at t equal to t naught. So we know what is the next point. We know what is the point in the next time t. So we'll have another wave function in time t equal to t naught plus delta t, let's say. So we know how how this wave function psi x t naught moves, as psi x t moves. Once we know psi x t naught, once we know psi x t naught for all values of for all x, so it's completely deterministic in time evolution, and the probabilistic nature only comes in uh, this probability density of finding the particle at particular position. So this is the probabilistic nature at t equal to t naught, because we cannot tell where the particle will be. So this is a measurement problem, and this is called the kind of measurement related to the measurement postulate of quantum mechanics. And this is also known as the Copenhagen interpretation of quantum mechanics. Now, since this is completely deterministic, we start with a particle probability, and this thing mod of psi x at t naught square dx is equal to 1. Now, the Schrodinger equation will itself tell, and it's a homework problem, like using only the Schrodinger equation, uh, prove that if psi x t naught is a solution, then psi of x t dx square is on for all t. So it's deterministics in time evolution of xt, both in past and in future. Because if we know the wave function now, we also know the wave function before some time, and also know the wave function after some time. So it's completely deterministic in past and future. So now if we start with the wave function which is already normalized, now using the Schrodinger equation, you can show that the normalization will be true uh, for all time. And this is actually a very important, is called the probability conservation or unitary time evolution. So important that you can postulate it and derive Schrodinger equation, which looks like h of psi equal to I h bar d psi dt, where h is the Hamiltonian operator, which is related to another operator called u, which gives the time evolution of wave function, and you can construct this h construct the Hamiltonian H from this U, which is the time evolution operator. And if U is unitary operator, then you can construct the time Hamiltonian from there. And which is the viewpoint of like from unitary time evolution, you can get the Schrodinger equation, which is nothing but the conservation of probability. And the sixth thing is, and the next thing is continuity equation. What is continuity equation now is rho, which is the probability density. Now, if I have a particle and let's say that the particle is electron. Now, finding the electron, the probability of finding the electron can be related. So now let's say particle is electron and we have many 10 to the power 23 Avogadro number of electrons in a material. So each electron is individually given by individual. The dynamics of each electron is given by this one particle, one electron Schrodinger equation. Let's assume that thing, and let's assume that each electron has a probability of finding somewhere. So since I have many numbers of electrons, so I'll get a kind of a density of electrons. So my charge density will be the charge of electron and this probability density. And since we know from Maxwell's electromagnetic theory that charge density satisfies this continuity equation, and this is already in the Maxwell's theory, then we expect that it will also satisfy some kind of continuity equation, del rho del t plus del dot j basically. But since I have only one variable, let me write down j is equal to 0, and we have to find out what is j. Let's call it j of x in the x direction. Now, before that, I just want to emphasize that this continuity equation is very important, and so I'll just give you. I just want to show you the continuity equation for Maxwell's electromagnetic wave. Maxwell's equations. The first equation is, so I'll use the Maxwell's equation in free space. You can do it. The homework, do it for Maxwell's equations in some medium. So in medium means we have this displacement vector and h. So in Maxwell's equation in free space is rho by epsilon naught del dot b equal to 0. So I mentioned this is Gauss. This is no magnetic monopole. This is Faraday, Lange, and others. This is of course Coulomb and others. Similarly here, and the fourth one is del cross p is mu naught j plus mu naught epsilon naught d by dt. But what this Maxwell's equation is telling you, the Maxwell equation is telling you if you know the charge density rho and the charge current density J, then you can calculate electric field and magnetic field given boundary condition. These are also partial differential equation in boundary condition, but once you know, and this is your source basically. This is your source. But this Maxwell's equations is a surprise, and this is known as Ampere-Maxwell's law. Ampere, Biot-Savart, and Maxwell. Others and Maxwell. We have these four laws, four equations, but these four equations actually put a constraint on the source. Constraint on the source. The source rho and j cannot be anything. Source, it looks like the source can be anything, but constraint on the source, and the constant we will get by taking this derivative of this equation. So del rho del t is equal to epsilon naught d dt of del dot e, and I can change the order of the derivative del dot d dt, and I can substitute d dt from here, which will be divided by mu naught, which will be epsilon naught del 1 by mu naught del cross b minus a. So epsilon naught d dt, basically I was substituting this thing. Which gives del rho del t plus, if I take this term del dot j on the other hand side, del dot j is equal to del dot del cross. Now that is 0. Now if instead of del, if you have some vector a cross b and taking the dot product with that vector, so this a cross b is perpendicular to a, so that vector should be 0, and that's again true for this operator delta. So you get 0. So that is very important in that you have a continuity equation. So similar continuity equation should hold, because if Schrodinger equation actually describes the electron, the properties of electron, similar continuity equation should hold, and we should calculate the current J here. Should be able to calculate the current J here, and this is calculation. So I'll just mention how we will do that, and then you can do that yourself. So again, Max's Schrodinger equation. Now we are talking about Schrodinger equation. IH d psi dt is equal to minus h bar square by 2m d2 psi dx square of psi plus v, which is only function of x, of psi. Psi is a function of x and t. Now, since you have this Schrodinger equation, you can take the complex conjugate and make conjugation everywhere. You can write the complex conjugate version of the Schrodinger equation. Now, Vx is real. It's very important. Psi star. Now you have you can calculate what is d rho dt, and you have defined rho is psi star psi. So that will be d psi star by dt times psi plus psi star times d psi by dt. And from this first equation, you substitute the second. Do it. It's not difficult. From the first equation, you get 1 minus I by minus 1 by I h bar. and you get the entire thing. Minus h bar square by 2m d2 psi star by dx square plus b psi star times psi. And the next one you get plus 1 by I h bar, the entire thing. Psi star times minus h bar square by 2m d2 psi by dx square plus b psi. And surprisingly, minus 1 by I h bar v psi star psi and plus 1 by I h bar psi star v psi, these two terms cancels. And what you are left with is plus 1 by h bar by 2im t2 psi star dx square psi minus h bar by 2im psi star d2 psi by dx square, which is h bar by 2im ddx of d psi star dx psi minus psi star d psi dx. And this must be equal to ddx of j of x with a minus sign, because d dot lt will plus there, so we get j of x is equal to h bar by 2im psi star d psi dx minus d psi star by dx psi, which you can write down as the h bar by m of the imaginary quantity of psi star d psi dx, because imaginary quantity of any complex number is equal to g minus g star by 2, imaginary part. So imaginary part is actually a real number, but yeah. So that is your current density. So indeed we have an expression for current density, because why this all of this is necessary, because when we will try to derive the transport in devices, we'll use this formula. This is a very important formula, and the idea behind this is, again, it's a probabilistic viewpoint. And if you think of many electrons, and they are given by the this one particle Schrodinger equation, and they are independent, then you can think of that probability is nothing but for the electron density will be governed by the probability density. This is exactly now an important consequence. So is called the stationary states. So the stationary states of the Schrodinger equation I have abbreviated the notation. The stationary state of the Schrodinger equation is again, so now stationary states is when you can separate the variable. So this is a partial differential equation. This is a partial differential equation. Psi of xt is a function of both x and t, but when you can use the separation of variable. Right, the psi of xt is let's call it a big psi, big psi of xt is small psi of x times phi of t. You can separate the position and the time variable, and if you can separate the position and the time variable, what you will immediately get is 1 by psi minus h bar square by 2m dx square psi, and this psi only depends on x, plus bx psi of x is equal to I h bar by phi of t, and this has become the space derivative only, time derivative only, d phi by dt. And since this side is a function of x only, this side is a function of t only, both sides can be equal if they are equal to some e, and then we'll get d phi by dt is equal to minus I e by h bar times phi, which will give equal to phi of t is exponential minus I e t by h bar. So immediately you know that your total wave function psi of xt is some psi of x and e to the power minus I e t by h bar, and so what is rho of xt? Rho of xt is this psi square, which is modulus of these things, but modulus of these things will be 1. So if I write down psi star x e to the power plus I e t by h bar times psi x e to the power minus I e t by h bar, but this cancels, so we get only psi of x square, which is independent of time. So the probability density does not change with time. Probability density is stationary. Doesn't change. And that's why this is called the stationary states, and it will always happen no matter whatever age your age is. So it's a homework. If such separation of variable can be made in h of psi xt is equal to I h bar of time derivative of psi of xt, and this is some general operator, and you don't know any general, some Hermitian operator, and I'll talk about what is Hermitian operator. If you can do this separation of variable, then rho of xt will be time independent. You can easily check that. So that's why it's called the stationary states. Okay, so I'll just stop here and stop for some question answer session. So do any one of you have any question? You can ask, because I talked a lot, I think. So it's a good time to stop now and for a question. Okay. Hi, Dr. Krishan Das Gupta.
Hello, sir. Good afternoon, sir. Sir,
afternoon.
I want to know that only separation of variable is responsible for stationary states or anything else. Means,
okay, no. Okay, separation of variable, and also that Hamiltonian should be time independent. Your Hamiltonian should be time independent, because I am sharing this, right? And also your age is time independent.
Okay.
Because if your H is time dependent, then we will have time dependent perturbation theory, then there will be transition from one state to another. Because if H is time dependent, then you have a function of time here, right? If V of X is time dependent, let's say, if V
Okay.
of X was time dependent, then we could time dependent, right? Then the
Okay.
reasoning I gave, this is only function of X, will not be valid, right? When this is only function of X,
Yes.
this is only function of T, I will say this is some constant. And once I
Yeah.
get some constant, this part is already fixed. So that for that, this is function of X means your H is time independent. So when I'll talk about Fermi-Golden rule. Fermi-Golden rule is nothing but transition from one state to another, because your H is time dependent. So this is actually also necessary. It's very good questions, and yeah, H is time independent is necessary for stationary states. And stationary states, yeah, you will find by this separation of variable. Once you can separate this variable, then of course, if you can solve it by separation of variable, then there will be a stationary state. At least for the Schrodinger equation, the probability will always be time independent. If you have time independent Hamiltonian, you will always be able to find the stationary states. Is it clear, your question?
Yeah, sir. Thank you, sir. Means, sir, if H is Hermitian and time independent also.
Hermitian is always there, because that will be already in the postulate of the quantum mechanics that I am going to talk about now, the postulates of the quantum mechanics.
Okay.
But even we being Hermitian, it can be time dependent, right?
Yeah.
So yeah, so
For
time,
stationary states, it's always should be a time independent
yeah,
Hermitian operator.
yeah.
Okay. Thank you, sir. Thank you.
Hello, sir.
Yeah, hi.
Sir, you said when potential energy is time independent,
Yeah,
and if V of X is real,
yeah.
wave functions can't be real. What does that mean, sir?
Oh, okay. The total wave
Second point.
function, the total wave function cannot be completely real. So you don't confuse the wave function that you plot like sine x, cosine x. That is the only the special part. I am talking about the total wave function, capital of psi. Let's call it, yeah, the second part. Yeah.
Second point,
X
sir.
is this that okay. Psi of x comma t cannot be real, because if psi of x t comma t is real, then the left hand side itself is real, right? Purely real. I mean, real is real, and the right hand side is purely imaginary. Because psi of xt is real, time derivative will give you another real function, and you are multiplying it by a imaginary number. So it's it will be purely imaginary, and the left hand side will be purely real. So psi of xt, which is the total wave function, cannot be real. Because
Okay, sir.
remember, the
Yes.
total wave function always has these two parts. If this separation of variable and you are a stationary state can find a stationary state, then it always has these two parts, right? There you have this imaginary time evolution, right? There you have
Yes,
this
sir. Yes, sir.
imaginary part.
Yeah, I understood, sir. Now. Yeah.
Okay.
Thank you, sir. Thank you.
Yeah. Thanks. Okay, I think.
Good afternoon, sir.
Yeah, Dr. Ragini Tripathi.
Yeah, sir.
Okay, hi.
Yeah, sir. I have a very silly, just a basic question.
Yeah, sir.
That in many of the books it is written, sir, that psi don't have any physical significance, right?
Psi don't have any physical significance.
And psi mod of psi square, they do have the physical significance.
No, yeah.
So, but sometimes I get confused that why do we say that psi don't have any physical significance?
No, it's the wrong thing. No, it has complete physical significance, because you are determining psi itself, right?
Yeah, we are just representing wave through that function. So there must be some significance.
Yeah, psi has physical representation. So that is another thing that is again related to which is called gauge invariance.
Okay.
So gauge invariance is a property in electromagnetism, but gauge invariance means you change scale and you physical property does not change. And in case of Schrodinger equation, which it means is that we only care about the function psi of xt. So if I have two functions psi of xt, and if I multiply it by some constant, where alpha is some constant.
Okay, it
Times
means That whatever is
yeah, if my new psi tilde of xt is some pure imaginary number, this is a not pure imaginary number, it's a pure phase, and this e to the power I alpha is called pure phase.
okay, pure phase.
Then
So
I
we do
cannot
have,
distinguish, like both my psi of xt and psi bar of psi tilde of xt gives us the same physical property. These are just related by a gauge transformation. So gauge transformation, you know about electromagnetism, right? In
yeah,
electromagnetism, simple potential. So electromagnetism is a simple electrostatic potential. That you know that electrostatic potential phi prime equal to phi plus some constant c gives you the same electric field, gives the same electric field,
yes, sir.
right?
Yeah,
In electrostatic, even in the electrostatic potential, you know about this. So this is nothing. So does phi have physical significance or not? Yes, of course, phi has physical significance, but some information is phi is irrelevant. We don't. I mean that information is phi can be changed without changing the physical property. That's called the gauge invariance, or that's called the gauge transformation. So here the meaning is psi has physical significance only the pure phase. If I multiply by a pure phase, even the psi tilde doesn't matter. And surprisingly, then you can ask a question: what if I don't multiply by a pure phase? What if my alpha is also dependent on, and this is called R and T in more generality, most generality. So what if alpha is function of position and time? And surprisingly, you can see that if you combine these things with the gauge invariance of quantum mechanics, gauge invariance of electromagnetism, what you will get, which is known as the Schrodinger equation in an electromagnetic field. So I'll go through it, but let me answer the questions of some other participants. And is your question clear?
yeah, sir.
I mean,
Yes.
is the answer clear? Okay.
Yeah, thank
Okay,
you, sir.
thanks. Hi, Dr. Sanjeev. I see your raised hand.
Yeah, Dr. Rick. So
Yeah.
I have a question. Just means some
Yeah, yeah.
curiosity that this time independent Schrodinger equation
Yeah.
we apply it to particle in a box or some potential barrier, potential
Yeah.
well. But is there any example where we use the time dependent Schrodinger wave equation?
Yeah, time dependent Schrodinger wave equation is used, not used directly, because time dependent Schrodinger equation is very hard to solve. So how do you solve the
Okay.
time dependent Schrodinger equation? So there are, I'll just time dependent Schrodinger equation. The method to solve the time dependent Schrodinger equation is through the, so I talked about this unitary time evolution operator. I'm not going in details, which is
Okay.
applied
Okay.
to a wave function psi of xt naught will give you the wave function as later time t. Now, solving this equation is through, which is called as Dyson series. And we don't use the Dyson series, we truncate it in the first few terms and truncate it in the first few terms. Let's call the first term. And we get what is known as the Fermi golden rule.
Okay. Okay. Right. Right. Right.
Right.
Right.
So
Right.
we
Right.
use the time dependence property, and how we view Fermi golden rule is from a perturbative point of view. Perturbative point of view means we first solve a time independent Schrodinger equation. Let's solve a time independent Schrodinger equation first. Then we will get some wave functions psi1 xt, psi2 xt. These are different states. I didn't talk about the different states yet. These
Right.
are different
Right.
states. And then we think about that transition between these states and we calculate the transition rates, right?
Right. 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 Thank
And
you.
that is
Thank you, Doctor.
actually the time dependent Schrodinger equation.
Yeah. Yeah. Thank you. Thank you,
Yeah.
Doctor.
Okay. Any other question? Okay. So let's start. So now I want to give you the idea of commutativity. Idea of commutativity. So as I just mentioned, we treat this momentum P as an operator which is given by, let's call it momentum in the x direction, an operator which is given by minus I h bar ddx, and any function of x is given by another operator which is just multiplication of that function, which means that if momentum operator acts on a wave function psi, it will be minus I h bar d psi dx, and if the position operator acts on psi, it will be x times psi. So x times dot. X dot means is a scalar multiplication. Now we want to know whether they commute or not. What do we mean by commute? Commute means if we apply the operator one after another uh, uh, and in reverse order, then there should be equal or not. So commute means they should be equal. So if I have two operators, so now I'll denote operator by something like A, B, C, and so on. So the commutator between two operators A and B, and this is called the commutator, is by definition so which means that this commutator is also an operator. This is also an operator. So operator means is has to act on something. So this commutator operator of A and B acting on this psi will be how will we calculate that? So that will be acting. We'll calculate that in this order. So once I act with B with psi, we'll get a different wave function, and then I will act with A, or in the reverse order. Now let's calculate. So this is the definition of the commutator, and let's calculate what is the commutator between these two operators x and y. And this is very easy to calculate. Now whenever we want to calculate it, we want to calculate it by acting it on something. So this will be xp acting on psi minus p acting on x, which will act on psi. So now x acting on psi is just scalar multiplication. So I know that this is x minus I h bar d dx, which acts on psi, and this is minus I h bar. So you can plus I h bar d dx is acts on the entire thing, which is x, and x acting on psi. X acting on psi is just multiplied x of psi. So if you just calculate this, we can clearly see that from here we have an extra term which is I h bar psi of x plus I h bar x d psi of dx. We have this extra term, these two terms will cancel. So we'll get this is I h bar psi of x. So this commutator xp acting on psi of x is just I h bar psi of x. And this is written as in the compact form, the commutator of x and p is I h bar times the identity. And this leads to the famous Heisenberg uncertainty principle. That uncertainty in measurement position and momentum is greater than equal to h bar by 2. Why? So now we have to this is and last thing I want to mention is Hermitian operator. And the Hermitian operator definition is that before that I have to mention some concept of inner product and states or vectors. So in Dirac's notation, there is a useful notation which is known as the Dirac's notation. Dirac's notation mentions about the state of psi and written as Bra notation, and this is the state psi, and the representation of the states representations so this is an abstract state. This is a very abstract state there somewhere, and you want to represent this state. Let's say you want to represent this state in x position basis. So basically then what you get is the wave function which is written as xi, where this is nothing but kind of inner product. So inner product is if you have two vectors, you form the, if you have two vectors psi and phi, you form the inner product between psi and phi, like this. This is the inner product. So you, as you have a state psi, also you have this, also you have the states x, which are position states, position eigenstate, and then you represent in the x basis as the wave function. So this is a little higher theory, but we can use Schrodinger equations in position representation for the purpose of the course, and we don't need to go in details of the Dirac notations. But what is an Hermitian operator? So what is this inner product means? Inner product means the integral of psi star of x with phi of x. So basically the operator is Hermitian. Let's call H is Hermitian if this is true. So which means nothing but this equality to be true. This is an operator acting on this wave function. The proper limits. And you can check that this operator P with any function of operator, any function of at P square, they are all Hermitian operator. P square by 2m. So, they're all Hermitian. They're all Hermitian operators. So actually you can write it in a simpler form, like so basically the operator H phi So basically, yeah, correct it here a little bit. Correction. So Hermitian operator is if you take the inner product with psi with this h of phi, h on phi. This is a state basically, and you are taking the inner product. That should be equal to the opposite, which is h acting on psi. That's the state, and you are taking the inner product with phi. So basically, in notation, which is psi star, h acting on phi, psi star of x, h acting on phi of x, dx should be h acting on psi of x, and then we are taking the inner product. Then you can check that all these operators are Hermitian. Now let me mention the postulates. So before the postulates of quantum mechanics, there are some properties of the Hermitian operator, which is important because that comes into the postulate of the quantum mechanics. The first postulate of quantum mechanics is all observables are represented by a Hermitian operator. So like the first thing is the first postulate is that the state of the system is a vector in Hilbert space, which is complex, kind of complex vector space. And think of, because you have the complex number. And the second thing is every observable. And which are observables? The observable is that you can measure, like energy, momentum, angular momentum, spin, etc. Whatever you can measure, every observable is represented by, or is represented by a Hermitian operator. In the vector space, in the Hilbert space. There are many technical difficulties, because this Hilbert space can be finite dimensional or infinite dimensional, and then even the Hermitian operator and self-adjoint operator are slightly different and things like that. But kind of these are the postulate. Now there are some properties of the Hermitian operator. Now a Hermitian operator has some properties. So the first property of the Hermitian operator is it has real eigenvalues. Now what is an eigenvalue? The eigenvalue is an operator acting on the function e of x should be some number lambda times the function itself. So that is called, if there exists a function e of x such that this holds, then e of x is called an eigenfunction, and lambda is called an eigenvalue. Now I immediately don't want to give the example that what is the eigenvalue of this function, eigenfunction and eigenvalue of this operator p bar. So P bar is an operator which is minus I dx of psi. Now if you take e to the power I kx and operate with this, you will immediately get h bar k e to the power I kx. So h bar k is kind of an eigenvalue. And is e to the power I kx an eigenfunction of this operator? So yeah, you can think of, but there are many technical things like this is not normalizable and not normalizable. So you have many to change the definition a little bit and things like that. But this is kind of thing. That Hermitian operator has real eigenvalues, and the second thing is that the expectation value of this operator is real. What is the expectation value? So the expectation value is expectation value with respect to some state psi of x, let's say. So psi of x, which is represented like this, or you can think of as abstracted psi. So it's given by this inner product of psi of this operator, expectation value of any operator O, this thing. So which is nothing but psi star of x and this operator acting on psi of x dx with the same psi. So that is the expectation value, and if operator O is Hermitian, the expectation value is always real. And then you have this big postulate, which is the measurement postulate, and there are another properties, and there's eigenfunctions of Hermitian operator, and these are properties of the Hermitian operator. Is eigenfunction of Hermitian operator forms a complete basis of the vector space. Now again, what kind of basis is this? There are different kind of basis, like the basis we know. So there are different kinds. So there are mathematical technicalities. The basis we know, like x, y, z of a finite dimensional vector space, is different from the basis we know in Fourier series. So Fourier series, we can represent any periodic function by this formula, right? A n e to the power or n, let's say e to the power, or let's say sine n pi by l plus bn cos pi by l with the periodicity l, 2n pi by l with the periodicity l. So basically, this sine and cosine functions also form the basis. Whether these are the same basis or not, because this is numerable, you can count it, n equal to, you can count it 0 plus minus 0 1 2 3, but infinite number. So this is a, because if this vector space is infinite dimensional, so they are not the same kind of basis. But okay, so you can think, okay, so there are many subtle points here while talking about the mathematics, but this is kind of thing that you will learn basically. Eigenvalues are real, eigenfunctions form a complete sets of bases, and you can also change the basis, and you can also make the basis orthonormal by orthogonalization and normalization. Orthogonalization and normalization. And orthogonalization is one is Gram-Schmidt orthogonalization, that you probably have heard for finite dimensional vector space, but for again infinite dimensional vector space, similar process is there. You have to keep on doing it. So now the measurement postulate, the postulate is called the measurement postulate. The measurement postulate is if you want to measure, if you measure the observable O, the first thing you O is Hermitian. Now the result you will get, the result will always be the eigenvalues. The result of the measurement will always be one of the eigenvalues, always be one of the eigenvalues. You can, so you cannot get anything apart from the eigenvalues, and this is the key essence of discretization. So if you measure the energy, and if your energy has the discrete eigenvalues which are discretized, then you will get only discrete energy. You cannot get anything in between. You will always be, it will always be one of the eigenvalues. On average, you will get the expectation value. And when you will get the expectation value, now the thing is, if your state is already an eigenstate, then always the same eigenvalue, always the same eigenvalue. And if your state is not an eigenstate, then it will collapses to the eigenstate corresponding to the eigenvalue, collapses to the eigenstate corresponding to the eigenvalue that you have measured. And the best example of this is the Stern-Gerlach experiment that I in the Stern-Gerlach experiment, you have the Stern-Gerlach apparatus, South Pole, North Pole. This is your apparatus. Now, once you passes the electron, then electrons only place in one of the two eigenvalues, and we call it, one is plus half spin and another one is minus half spin. And when it goes to plus half spin, it goes to a state which is related to, so if this is aligning with the g axis, so it will go a state which is z plus, and it will collapses to a state which is z minus, irrespective of what was you have started with. So if you block this one and pass it with the Stern-Gerlach experiment which is in the plus x direction, then again you will get only one of the two eigenvalues, plus half minus half, but the eigenvectors in this state correspond to x plus and g plus, x minus, and x plus and g plus are related but they are not equal. And now again, if you take any one of them, block this and pass to another plus g, then again you will get only two. Why? Because now your state already has changed to something else. Although you started with this plus z state, because of the measurement, there is this collapse. collapse of the state is happening. That's why the state already got changed because of the measurement. So, and this interpretation, this collapsing state, collapse of state, collapse of the wave function, this measurement affects the states. So here you will get G plus and G minus. And this was known as the Copenhagen interpretation, but nowadays this interpretation is there are many other interpretations, and Everett many world interpretation is very popular nowadays. And to know a little bit about this interpretation, you need to know a little bit about superposition, and so I'll not talk about this superposition and entanglement. So the idea is not collapsing of the wave function, is entanglement of the wave function with the surroundings. That's the idea. These are mainly the postulate of the quantum mechanics. And if your if your state is not an eigenstate, it will collapse, and uh, you will get the result with some probability. Get the result with some probability. In this case, you will always get the same eigenvalue. In this case, there is a probabilistic interpretation. You will get the result with some probability, and the probability of obtaining that result is also given by a formula, and which is just the projection of that operator on that wave function. So, if your initial state is psi I, your eigenstates initial state is psi naught, let's say. Eigenstates are some eigenstate are ek. Then the probability of finding that is given by this ek psi naught square. So, and totally normalized. I have normalized. Which this is normalized. So yeah, so that's the idea. So basically, one example. I'll finish this session with one small example, which is particle in a periodic free particle. In a circle. So there is in a circle, so which is considered so the perimeter of length L, and this is the only x variable. You can also think about it as the theta variable. Theta goes from 0 to 2 pi, and periodicity condition is psi x plus is equal to psi x, and the if you solve the Schrodinger equation psi double prime x plus v is equal to 0, v of x equal to 0 is a free particle e psi of x. So psi of x will be to the power plus minus ikx, where p is h bar k. Energy is h bar square k square by 2m. So these are your because if you substitute by ikx after double derivative, you will get I square k square. I square is minus 1, h bar square k square by 2m. E will be h bar square k square by 2m, and momentum p is h bar k. Now any state will be superposition, can be written as superposition of eigenstate. So if I tell you, you start with a initial state psi naught, which is kind of a sine function. This is periodic, and the first you starting psi naught at x t equal to 0 is sine of x by L. Or 2 pi x, 2 n pi x by L, 2 pi x by L. Let's say sine of 2 pi x by L. It's not 2 pi, it's pi x by L basically, sine of pi x by L. So how your wave function will behave? So what will be the, so what is the, so if you have started with this wave function, what will be the energy, and what will be the what is the momentum, how the wave function will change? So everything will govern by this. So okay, let me go through more generality, like any wave function. So basically I had the concept of the stationary states. Stationary states. Now, if I have h of this psi of x is equal to e of psi of x, and if this is the eigenfunction equation, so I will have e k psi k of x, then I know the corresponding states. It moves like psi k of x e to the power minus I e k t by h bar. That's the time evolution of this state corresponding to each eigenfunction. Now I have a general state psi naught. I start with x at t equal to t naught equal to 0, and that I can write as superposition of all these states with some coefficient ak psi k of x. And why I can write it? Because this psi k form a basis of this Hilbert space, so I can write any function like this, and I will be able to find out all these coefficients. And once I find out that, then my psi of x at t, given psi naught of x of t, will be given by this coefficient, and how this psi k of x varies. The psi k of x varies like this, e to the power minus I e k t by a. And why this solves the Schrodinger equation? Because of linearity. Each of them solves the time dependent Schrodinger equation. So each of these functions solves the time dependent Schrodinger equation. I mean, it satisfies the time dependent Schrodinger equation, and these are linear combination, which I call the superposition. And because of the linear combination, this also solves the time dependent Schrodinger equation with the initial condition. So that is the most general theory, how the time evolution of any state in Schrodinger picture. So next I will give some example like finite square wave potential and infinite square wave potential, scattering and tunneling of states, and the particle viewpoint, how the particle viewpoint emerges in the next session. So do you have any questions? So I'll end the session here. Do you have any question?
Yes, sir. Hello.
Yeah. Hi.
Sir, my question is, what is the physical significance of spin?
Spin is an angular momentum. So,
Okay.
so spin is an angular momentum, nothing but spin.
Sir, there are many particles having spin 0, half, +1, and so on. Right? Then what do they have significance, sir?
So first of all, it's an intrinsic property. And okay. Let me. So it's an intrinsic property, and there are many. So basically, you. I mean, what is the significance? Means there are many particles with different mass. What is the significance of mass? Is you are asking similar kind of question, right? So angular momentum, it
Yes.
I mean, it interacts with magnetic field.
Okay, sir.
Because because you have an angular momentum, interacts with magnetic field if the particle is charged, for charged particle. I mean, of course, yeah. So for charged particle, classically, you know why it will interact with magnetic field, because classically for charged particle, so it interacts with magnetic field for charged particle. Even the classical mechanics, you know, if a particle spins around some axis and it has some charge, then it creates itself is kind of a current carrying loop, so it creates a magnetic field, right, around this current carrying loop, and so there will be magnetic field here. So, and since this gives a magnetic field, it will interact with another magnetic field. So this is the classical picture. The quantum mechanically also is a angular momentum is interacts with the magnetic field. It interacts with anything that creates a magnetic field. So spin is angular momentum. It interacts with the magnetic field, so it will also interact with angular moment, interact with orbital angular momentum, because orbital angular momentum is something that also interacts with the magnetic field or creates the magnetic field kind of thing. It will also interact with the orbital angular momentum, and that gives rise to spin orbit coupling. So there is, I mean, there is, what is the physical significance? It's not our asking what is the physical significance. It's our asking what are the intrinsic properties of my particle. What are the intrinsic properties of my particle?
Okay, sir. Thank you.
Right?
Hello?
Because that's always the case.
Hello?
Spin is an intrinsic property, and that's, I think, the most important thing to remember. Just like mass and other things, and it's a vector quantity, mass is a scalar quantity, and I think that's the only thing. I mean, that's an intrinsic property and response to something else. Okay.
Hello?
Yeah. Hi. I think many of you are.
Sir,
okay. Okay. Yeah.
Sir,
Yeah.
I have one query.
Yeah.
How to exactly define the quantum dots and what is the significance of it in quantum mechanics?
Okay, I'll
And what
talk
is
about that
importance?
quantum dots. Yeah, I'm just going to talk about that quantum dot. So quantum dot is when you confine an electron. Quantum dot is when you confine an electron in all three dimensions. Confine means you create some kind of a potential barrier. So quantum dot, quantum wire, and well. and so on. So, right.
So which is look like a potential barrier like that.
Yeah, it look like a potential barrier.
Okay.
So basically,
But that means a potential barrier, potential well, like that.
Yeah, you are. So basically, when you have, there will be a session on band diagram. So when you have band diagram, then you can draw the bands of the electron, right? The energy levels. And if you draw the energy levels, then you can actually see what is the potential of the electron. So like in a semiconductor MOS structure, so this is the band bending that you probably have seen, right? So I'm drawing the Fermi level. So here, what you are drawing, you are actually drawing the potential energy, and this is the potential energy of the electron at this interface, which looks like a triangular wave. So you model it by a triangular wave. So similarly, in heterostructures, when you are sandwiching two materials, you will get a band diagram like this. You may get some kind of band diagram like this for conduction band and valence band. So I'm drawing some band diagram. Material 1, material 2, material 1. So this is kind of a heterostructure. So here also you are getting a potential. What you are drawing is a potential diagram. So your electron is confined to this potential. At least in this direction, in the other direction is free to move if you make it so. Okay. So quantum well is
for
you
this,
are
confining
in one dimension, only. So you solve only one dimensional Schrodinger equation. I mean one dimension position, because in other two dimension what you solve is periodic boundary condition, and in the G dimension if you confine, if you, in that confinement direction you solve for whatever potential it is it. So if this is your confining direction, you solve it for a given potential Vx, P of G. I mean, if this is your confining direction, you solve it for a given potential Vx.
Yeah, okay, sir. For this, any experimental studies?
Yeah, there are lots of experimental studies on quantum dot, quantum well, and quantum wire. So this is a 2D system. This is a 1D system. So free to move in only one direction and two direction is, and this is a 0D system. So it's not free to move in any direction. So you have confined everything to kind of a box, particle in a box. And since you have confined everything, it has all kind of discrete states, and then you can transit from one state to another by changing the dimension of this system. You can change the energy levels between them, and then if you change the energy level between them, then by this transition you can emit light, and it has application in laser also. The quantum dot laser you probably have heard. So it has all applications, quantum dot, wire, and well. Does that
So
answer
my
your
final
question?
question.
Yeah.
So what is the best simulator for nanoelectronic devices?
So depends on what kind of. So if you want to include Schrodinger equation in your simulations, so there are only a few of them. I mean,
Yeah.
right. Because right now
Schrodinger
equation.
Simulator name. So the best simulator.
So what you want to
for device modeling and simulation? What is the best simulator? Device modeling.
You will find many simulators in Nano Hub which are free. So if you want to include like non-equilibrium Gibbs function, NEGF, then there are particular simulator in Nano
So
Hub.
that simulations are that simulators in Nano Hub are permitted to publish in journals.
Yeah, that's the open source.
That results.
Yeah, the results are. You have to mention their
Open
that
source.
you have used their code, but you can contact them also. But I think
Okay, in journal paper we have to mention the results taken from open source Nano Hub.
Yeah. But
That is permissible.
yeah, but if you want to build a complicated device, like what kind of device, like if you want to study a MOSFET structure, and if you want to include some quantum
Yes,
mechanical
yes.
effect, right? So
Yes, sir.
many of them you introduce quantum mechanical effect to Monte Carlo simulation. Then again, you have to write your own code, or if you have to write your own code for two-dimensional NEGA model or things like that. So in the nano hub, what you will get is, I think, simple toy model for one dimension or things like that. But again, you have many of them write their own code, like Monte Carlo simulation. You can include quantum effects for NEGF. You can include quantum. NEGF is quantum. So you have to write your own code. But then again, it's much more than I
Okay,
think
general
what you are.
people general people accept the results from nano hub.
Yeah, they kind of accept the result from nano hub.
Okay.
Or if
Thank
you
you,
have
sir.
some
Thank
need,
you.
yeah, okay.
Yeah.
Hi, Akshay. I think you wanted to say something. Akshay Kumar.
No, sir. Thank you, sir.
Okay. Is there any other questions? I thought many of them are trying to say at the same time a few minutes ago. So if hi.
Hello, am I audible?
Yeah,
It's Dr. Raghavendra. Sir,
yeah. Hi,
thank
Dr. Raghavendra.
you for your wonderful. Thank you for your wonderful talk. Sir, can you please share these videos on YouTube or PDF in PPT later?
Yeah, sure.
Okay, sir. Okay, sir. It's really useful information. Sir, thank you.
Yeah, thanks. Any questions from the participants? Any question from the participants? Okay, then I'll end this session.
Sir,
And thank. Okay, hi, Ram Prasad.
Sir, my name is Dr. Ram Prasad, sir. In particle in potential box, we are using from the Schrodinger equation. We are solving energy levels values.
Yeah.
But that place we are using Schrodinger time independent equation, sir. That place, any possibility is there? We are using to Schrodinger time dependent equation.
We don't need that because time dependent equation is like we want to only interested in the energy eigenvalues, because once we know the energy eigenvalues, then we know how any wave function will behave in general because of this linearity property and things like that.
Okay.
Right. So we are not actually, we are solving the complete equation, but nobody mentions that particularly that we are solving the complete equation, because for this system where your potential is time independent, or even for the purpose of perturbation theory, what you need only is the solution for time independent problem, because time independent problems gives you the time independent problems gives you the eigenvalues and eigenvectors, right? So the eigenvalues and eigenvectors, if you can see my screen, then the if you can see my screen, yeah, this eigenvalues and eigenvectors, you get it from the time independent equation. And once you know it, then you can solve anything, because if you are given a particular wave function, then you can calculate the time evolution of the wave function. Okay. Using this principle, this superposition, and this will be the exact time evolution of the wave function. And this is the easiest way to show you this time evolution. There are more formal ways by applying the time evolution operator, which is the unitary time evolution operator and things like that. But exactly you will get this same equation. So basically, this is the final result. So that's why you only solve for the energy eigenstates, because the energy eigenstates gives you the time evolution.
Yeah. Okay.
Okay, so any other question? Okay, thank you very much. Okay, I think one chat. Okay, thank you. So I'll end this session. I'll stop sharing.